if you go back to the history of artificial intelligence, you might know that in the 70s, they were all keen on it being, saving the world, and it flopped. And the reason it flopped is that you can, we all know how to walk. Well, hopefully we know how to walk, but it's hard to code up how to walk. It's hard to say, well, if my foot's here, then do this, or my foot's there, do that. And so that's why it failed. And when they were doing it, one of their best attempts was to translate, okay, I'm a robot, how do I get out of the door without bumping into the table, right? They translated into a big logic sentence, and then they needed to know, well, are these logic sentences, how do I satisfy them all, right? How do I get my robot out of the door? How do I satisfy them all? And it turns out that what was also happening in the 70s is people like my father were starting to convince themselves that finding a satisfying assignment for these things is actually what we call NP-complete, meaning the only algorithm we have for it takes exponential time, and sort of just brute force looking for a solution is really hard. And so if they needed to do a brute force, they did that tree sort of lookup, which we talked about before, and I had 1 million slides on it, and I condensed them down to a few slides. So that's called Davis-Putnam. But another method that they used was if the sentences fell in particular, they looked a particular way, then they're called horn clauses. And there's a linear time brute force algorithm for solving horn clauses. And we're gonna cover it here, partly because it's fun and maybe because it's historic. I don't know if they still do this or not. They probably still do. But anyway, let's go back to the game of flu. If you know the game of flu, right? So we're going to consider two types of clauses, two types of statements. The one statement is where you have all your variables, and you have it implies, and on the left-hand side of the implies is you have the and of a bunch of variables that are not negated. Just to let you know, in general, if you don't have negations, then everything's what they call monotone, and life is much easier. As soon as you add negations, it makes things harder. So here, this has no negation. And what it says if all the facts on the left are true, then the fact on the right also has to be true, right? If one of them facts on the left is not true, then we don't know anything. The statement is true without knowing anything about the rightness, right? So, and here's another type of clause which says it's an or of negations. So it says this is not true, or this is not true, or this is not true. I'm not telling you which one's not true, but at least what it's saying is at least one guy from the list has to be false, right? So these are the only rules we're going to allow, and so here's a bunch of them, right? And our goal is to say, oh, by the way, if you're wondering about the arrow, why I use that arrow and not the more implies arrow, I should do a global change of these. It's actually because I made these slides before I started teaching logic. I made them for the algorithm class. All right, so this is just an implies. All right, so what we're looking for is, can we set all these variables in a way that makes them all true, right? And you think, oh, how do I start going about doing it, right? There are a lot of settings. right? And let me tell you a fun fact. It's always good to start where you want to start. Well, so this is just saying we're going to greedily set things. But let's just start with everything being false, right? Suppose that nothing is true, right? Now, what do we get? We get, well, these are called positive implications, and they're all true. Why? Because the left-hand side is false, right? If everything is false, then the left-hand side is false, and so all our implications are fine, right? And so similarly, these guys are all true. Why? Because they're all negations. And so all the negations are true, right? Everybody see that? So was it easy to find an assignment for these? Yeah, we just turned everything to be false and we're done, right? All right, so that wasn't so interesting. So let's add one more statement up here. Now, let's think about what this statement says. It says, if the stuff on the left is true, then the stuff on the right is true. But what's on the left? Nothing's on the left, right? So then you have to ask yourself, well, if you have nothing on the left, does it default to true or does it default to false, right? And we're going to have it default to true, partly because we have, you know, in these other guys, we have ands, right? And if I'm giving you a list of things and one of them is false, right? This and this and this and this and this, and one of them is false, it goes to false forever, right? So once you get false, you're in trouble, right? So when we start with the empty set, we want to say true, right? I'm going to say everybody on the left, right, is true. Why? Because there's nobody on the left, so they're all true, right? All right. So what does this tell me? It tells me that if we're forcing things, then that forces X to be true, right? So in any universe where these are all true, X is forced to be true, right? In fact, let me just sort of slip here another little story. In Pin 19, there were 5 sections and we needed a common exam. And one of the professors submitted a sentence that the requirement was to satisfy it, find a setting of the variables that makes the whole thing true. And if you did table lookup, it would have been really long because there were lots of variables. But what I observed was that you could start forcing things to make the whole thing true. It was an and, so this had to be true. So that could force variables, and that could force variables. And so I did cheat a little bit. I did a review class, and we kind of covered forcing of variables the day before the exam, which hopefully helped people. So here, we forced X to be true, right? And there, so now we can plug in true for all of these things, right? And we can kind of simplify and say, well, that's great. So what does that do to us? Anybody see the next thing that gets forced? Y, right? Everybody see how now Y is forced, right? So then we can plug in Y everywhere. Well, now we have X and Y true. So that then forces Z, right? And then we plug in Z, and that forces L1. And so, oops, if L1's true, then this is false, but it's an OR, right? So it doesn't kill us. It just drops this out. We can simplify it by dropping this guy out, right? He's no longer, this one here is no longer going to save this to being true. So then L1's true. So I don't know, we got various forces, and you keep doing the forces, and then you're here, right? And so now what do we got left? All the ones that you forced, all the implications that you forced are satisfied by forcing them, satisfied them, right? Now you didn't satisfy this one yet, right? Because we don't know about W and we don't know about W3. But after we force everything, then what's left, we're going to set to be false, right? And if we set W to be false, then that makes this sentence true, right? And similarly, you come down here and you'll see, oh, we killed off the guys crossed in red, but we didn't kill off this guy. This guy we can make to be false. Here we can make L3 to be false because we made W to be false. And so we satisfy it here. Oh, and we made W false, so it satisfies it here. Right? Everybody see that? So we've managed to satisfy all of these. And then we code that into our robot, and our robot manages to walk out the door. Right? All right, so that's good. Now, let's change the problem, right? So what I changed is I got rid of the W here, right? Now, can we satisfy these clauses, all of them at the same time? You got to know, right? Why no? It's because the things we force are still forced, right? We don't have a choice about that. If we want to satisfy that implies X, we got to make X true. And then that forces other things. And then in the end, well, if we want to satisfy those upstairs, then we're forced to make this false, right? And so these clauses we proved aren't satisfiable. Right? Does that make sense? Right? So this says here, maybe there's another thing. Don't panic yet. Maybe we can set variables in a different way to make them true. But the answer is no. This greedy, we did kind of what we did with greedy, right? You force things as you needed to. And that's in fact why in the third year course we have a whole section on greedy algorithms. And that's why we cover this. Right?